Right, these are notes 8E on normal distributions. All right, you may have heard of bell-shaped curves. Statisticians call these normal models or normal curves. Normal models are appropriate for distributions whose shapes are unimodal, that means one high point, and roughly symmetric. Normal models give us an idea of how extreme a value is by telling us how likely it is to find one that far from the mean. Normal distributions occur naturally. Like I said, heights of American men or American women are normally distributed. Many standardized tests are normally distributed. The weight of a Granny Smith apple is normally distributed. So the majority of the data is found around the mean, and then as you get further and further from the mean, you're going to have a less likelihood of those values occurring. All right, the normal model follows what we call the 68, 95, 99.7 rule. It's also called the empirical rule. So if we know we have a normal distribution, our percentages are going to follow that rule. So 68% of the data is going to be within one standard deviation of the mean. Your standard deviation is your scale. You talked about standard deviation in Algebra 1. So the mean is in the middle of our distribution, and then our scale is our standard deviation. So we add and subtract. Okay, so 68% of our data is going to be within one standard deviation of the mean. 95% of our data is going to be within two standard deviations of the mean. And 99.7% of our data is going to be within three standard deviations of the mean. So if we think about heights again, that's why we have very few extremely tall people or extremely short people. Now, so this empirical rule, you have to memorize. All right, here's another way of representing on the second drawing here. And this is probably a more useful way to memorize this. Let's talk about where those numbers come from. All right, this thing is symmetric. So 68% of our data is within one standard deviation of the mean. If we split 68, we get 34 and 34. All right, let's move out further. All right, so we get 95% of our data is within two standard deviations of the mean. If we subtract 68 from that, that leaves us with 27. Here again, it's symmetric. Half of 27 is 13.5, 13.5%. All right, continuing out, same difference here. All right, so we're going to subtract 99.7, subtract 95%. We're going to be left with 4.7%. Here again, split that. So 2.5%, 2.5%. Now, the area under the curve totals 100%. So we've got 100 minus 99.7. That leaves us 0.3%. Here again, split the difference. So that means the tails are 0.15%, 0.15%. Like I said, this is memorize this breakdown or be able to find it quickly. All right, here's kind of a neat illustration of a normal curve. It's called a quincux. All right, so here so the ball's hit and they have a 50-50 chance on dropping on either side of the peg. Let's speed this thing up so you can see what's happening here. Let's go really, really fast. All right, look at the curve it's making at the bottom. See how that's kind of a normal curve? So here again, so it's a naturally occurring event. So most of the balls are going to fall toward the middle of our quincux, and fewer are going to fall on the ends. So just like I said, just an illustration. And you see that normal curve developing, that mound-shaped, bell-shaped curve. All right, let's look at some properties of our normal curve. All right, so let's see. All right, we already said this. It's bell-shaped. And it's symmetric about a vertical line. X is equal to the mean. We're going to use the symbol X bar to represent our mean. The mean, median, and mode are the same and are located at the highest point. 50% of the data values are greater than the mean, and 50% of the data values are below the mean. It approaches but never crosses or touches the x-axis. So that's an asymptote. The area under the curve is always 1. It's called a density curve. If you take AP Stat, we'll talk a lot more about that. All right, let's talk about 6. We'll talk about the standard normal curve. It's the grandma of all curves because every normal distribution can be related to the same scale by using what we call a standardized score, your z-score. You talked about that in Algebra 1 too. Now, in the standard normal curve, all right, the mean is 0 and our standard deviation is 1. So the scale along the bottom changes, but the numbers in the body of your curve always stay the same. So it has a mean of 0 and a standard deviation of 1. Now to change everything to the same scale, we need our z-score, standardized score. So it's going to be x minus the mean over our standard deviation. All right, take a moment to talk about symbols. S represents sample standard deviation. And you notice that our notes are using this symbol, that's sigma, and that's population standard deviation. So right now, there are just 2 different symbols to represent standard deviation. Here again, if you take statistics, then we'll talk about the difference, more in difference about that. Okay, let's look at some problems that we're going to do with this. So here we go. We have the annual rainfall in River Heights has a normal distribution. All right, to do this, you must know that you have a normal distribution. All right, we're going to set up. So here's our work. We're going to set up that curve, and that's going to be our math, our work for this. So it has a mean of 78, so that goes in the middle, and a standard deviation of 10 centimeters. So that's our scale. So that means we're going to add 10 each time, and then subtract 10. Whoops, let's do that correctly. 58. Okay? All right, so the scale across the bottom is going to change according to the problem. Now the body of the table is going to stay fixed. So those are those numbers we talked about before, the 34, 13.5, 2.35, and these are all percentages. So do not, make sure you put the percent sign behind them, and the 0.15%. The numbers in blue are going to stay the same each time. The number across the bottom, the number in reds are going to change according to the problem. All right, this is all your setup. So get your curve set up first. Now answer the question. What percent of the time will the city get between 68 and 88 centimeters of rain? All right, so we want the area under this curve. This is our percentage. So if we have our setup, it becomes really easy. We're going to add 34 and 34 and get 68%. So 68% of the time, the city gets between 68 to 88 centimeters of rain. Okay? What could be easier? Now you have to memorize those numbers, okay? I will show you how to use a calculator in class, but right now, like I said, we need to memorize those numbers. They will not be given to you on the SOL. All right, let's look at another example. Scores of a college entrance exam are normally distributed with a mean of 550 and a standard deviation of 30. All right, so let's set up that curve. So 550, and this time our scale is 30, so we're adding 30 each time. And then subtract 30. Okay? All right, let's see what we want to do. What percent of the time will a student get into college with a score of less than 520? All right, less than 520. So you're looking for this area under the curve. All right, so what values correspond to that? So let's see, this is 13.5, 2.35, and 0.15. So I'm going to add those 3 values together. So take a moment, add those 3 values. All right, you should be getting 16%. So 16% of the time, a student will get into college with a score of less than 520. Now you might be asking yourself, what happens if we don't fall on those nice values? Well, that's where our calculator is going to come in. We can make an estimate using our chart or curve here, but to get an exact value, we're going to have to use a calculator or a chart. But since we have the calculator, I'm going to show you how to use the calculators in class. So we'll come back and do these with the calculator too, so you understand that, so you have that option. All right, let's look at another different type of example. The scores of a college, so this is the same best basic setup. Normally distributed with 5, 50, and 30. Okay, so let's do our curve again. So we got 5, 50, and a scale of 30. Okay, there's our setup. You score in the top 2.5% on your entrance exam. What is your score? All right, so this time we're looking for our answer is going to be one of the numbers across the bottom. So we got to, what area under the curve is going to correspond to 2.5%. Now, since we want the top, I'm going to start on the right side. So I'm going to try to accumulate enough area to get 2.5%. All right, so let's start counting. So I got 0.15%. Well, that's not enough. I know this is 2.35%. If I add those two together, I'm going to get 2.5%. So that means my cutoff is a 610. So that means if we score, so you need a 610 or higher to score in the top 2.5%. So there's another type of question, kind of going backwards. So that's why on the calculator we call this inverse norm. Like I said, here again, I'll show you how to use your calculator to find these answers also. All right, let's go to a different type of question. This was on an old SOL. All right, it says the data summarizes the test scores of 25,000 students. The data is normally distributed with a mean of 83 and a standard deviation of 3.5. All right, let's take a minute and set up our scale. So 83 and our scale is 3.5. So we're going to add 3.5 each time. And then subtract 3.5. Okay, take a moment, make sure you got your scale. Mean always goes in the middle, and your scale is your standard deviation. Shade the region in the curve where only the data for approximately 3,963 are located. All right, let's go ahead and put in our percentages. Remember, those are locked in because we have a normal curve. By telling us it's normally distributed, that locks in these numbers. And hopefully you've already memorized them, because like I said, if you write them each time, it kind of forces you to memorize the numbers. Okay? All right, let's look at our question. We want to shade the region under the curve where only the data for approximately 3,963 are located. Well, we need that as a percentage. So we're going to divide that by our total number of students, at 25,000. So this is going to give me 0.158, or 15.8%. So we need to figure out, we need to shade that region. We want to shade 15.8% of our curve. All right, so let's think about what we've got here. Well, I don't want to have anything to do with the 34s. That's too big. So I'm not going to use the 34s. Let's start with a 13.5%. If I add 13.5% plus 2.35%, That's going to be 15.88 or 85. Okay, that's going to be pretty close. Okay, if I add 0.15 more, that's going to be too small. I think actually that when I round this out, I can take it out to another decimal place. Okay, so that means I can shade these two regions. It's going to represent as close as I can get to that 15.8%. So that's one possible answer. But it didn't say the upper end or the lower end, so that means I could have also shaded the lower half, the 15.8%. So I could have shaded these two regions. This was the type of question where you got to click the regions on the SOL. So this problem has two possible answers, not different answers, two possible answers. You wouldn't want to shade both regions because that'd be too much. Okay, but like I said, it doesn't say lower or upper, so that's why we have two possible answers for this particular problem. All right, like I said, in class we're going to talk about how to use the calculator, because if we don't hit those cutoff marks, those standard deviation marks, the best we can do is estimate. So we're going to also show you how to use your calculator. All right, these are the commands we're going to be using. So you can try this if you have your calculator at home. All right, let's look at one more type of question that you're going to see that's been on the SOL before. Suppose a student takes two exams, getting a 55 in a verbal test and a 60 in a numerical reasoning test. The class scores for each test are normally distributed. For the verbal test, the mean is 50 and a standard deviation of 5. For the numerical test, the mean is 50 and a standard deviation is 12. Now it's plain to see that the student did above average for each test and did better at numerical reason. But our question is, how did this student perform relative to everyone else? So teacher says you're going to grade on a curve. This is what grading on a curve comes from, a normal curve. So compared to the rest of the class, which class did you do better? All right, since we have two different tests that we want to convert to the same score, this is when we use that standardized score, your Z-score. So we're going to find the Z-score for our verbal and also the Z-score for the numerical reasoning. So let's find the Z-score for both. All right, your score goes first. So the student got a 55 on the verbal with a mean of 50 and a standard deviation of 5. All right, do this math. So we get 1. Now your Z-scores tell you how many standard deviations you're from the mean. We'll put that on a scale here to make a direct comparison. All right, let's do the same thing with our numerical. So the student scored 60 with a mean of 50, but a larger standard deviation of 12. That means the score was more spread out. All right, so we're going to do this math. You're going to get 10 over 12, which is 0.83. All right, since we converted this to a normal curve, a normal standard curve, that means our mean is 0 and our standard deviation is 1. Your Z-scores tell you how many standard deviations you are from the mean. All right, so the Z-score for the verbal is falling here at 1. So here's this verbal, but the numerical is falling at 0.83. So since you're further away from the mean at your verbal, that means compared to everybody else in the class, you did better. Okay? So let's say, so a Z-score converts everything to the same scale, called a standard normal curve, which has a mean of 0 and a standard deviation of 1. All right, please write down any questions so we can discuss them in class.